In this chapter, we're going to learn about redox chemistry or redox reactions. Now, the term redox is actually made up of two words. Ox stands for oxidation and red stands for reduction. So the first thing we need to learn is what is oxidation and what is reduction. In chemistry, there are 4 different ways in which we can define oxidation and reduction, and these are the 4 ways. In terms of oxygen gain or loss, in terms of hydrogen gain or loss, in terms of electron gain or loss, and lastly in terms of the oxidation state of an atom, whether the oxidation state increases or decreases. So what do I mean by that? Now let's look at the first definition, gain or loss of oxygen. Now when a substance gains oxygen, we say that it is oxidized, we say that oxidation has occurred. When a substance loses oxygen, we say that the substance has been reduced, we say that reduction has occurred. The second definition is as follows. When a substance loses hydrogen, we say that it is oxidized, we say that oxidation has occurred. When a substance gains hydrogen, we say that reduction has occurred, we say that the substance has been reduced. The third definition is in terms of electrons. When a substance loses electrons, it means that oxidation has occurred, it means that the substance has been oxidized. When a substance gains electrons, we say that the substance has been reduced and reduction has occurred. Now the last definition is in terms of oxidation state. At this point in time, oxidation state is, we have yet to define it. Alright, we'll define it later on. For now, just have to know that oxidation occurs when the oxidation state of an atom increases, and reduction occurs when the oxidation state of an atom or a substance, an atom in a substance, decreases. But as mentioned, we will look at definition 4 later on. So once again, these are the 4 definitions of oxidation and reduction. One way in which you can remember is by this mnemonic SHU. Alright, S stands for oxidation state, hydrogen stands for, or H stands for hydrogen, O stands for oxygen, and E stands for electron. So the 4 letters make up the word SHU. Next thing that I want to point out is this, that definitions 1 to 3 are what I call the convenient definitions, meaning you should only use them if convenient. Alright, I will emphasize that slightly later, meaning when in a reaction, if you can see very conveniently that something has gained or lost oxygen, then you use that definition. Sometimes in some reactions, it's not obvious whether a substance has gained or lost oxygen, whether a substance has gained or lost electrons, hydrogen, then we should not be using these definitions. But the definition that will work in for any reaction, in any case, is definition number 4. So if given a choice where they don't state that you need to use any definition, I would say that definition number 4, I would recommend using definition number 4 because it's the one that is the most valid of the 4. So here are examples of oxidation and reduction using the first definition, gain or loss of oxygen. So if you look at the top half of the slide, I hope you can see that the substances in red, or the underlying substances, have gained oxygen through the reaction. So therefore we say that these substances have been oxidized. If you look at the lower half of the slide, I hope it's obvious to you that the substances in red, or the underlying substances, you can see that they have lost oxygen through the reaction. So therefore we say that the substances have been reduced. Now, one reaction that I want you to pay attention to is this particular reaction. As mentioned, in this reaction, copper 2 oxide has lost oxygen through the reaction. So we say that copper 2 oxide has been reduced. Now, at the same time, I hope that you can see the other reactant, zinc. Through the reaction, zinc has gained oxygen. So we say that zinc has been oxidized. Now, through this reaction, the point that I want to highlight is this, that oxidation and reduction, they occur together. Meaning, in any reaction, when something is oxidized, the other thing must be reduced. There must be something that's reduced if something else is oxidized. So oxidation and reduction must occur together. Now we look at examples for the second definition, gain or loss of hydrogen. In the top half of the slide, I hope that you can see that the substances in red, they have lost hydrogen through the reaction. So therefore, we say that these substances have been oxidized and oxidation has occurred for these substances. In the bottom half of the slide, I hope you can see once again that the substances in red, or the underlying substances, have gained hydrogen through the reaction. So therefore, we say that these substances have been reduced or reduction has occurred for these substances. Now we look at the examples for the third definition, which is the gain or loss of electrons. Once again, in the top half of the slide, I hope you can see that the substances in red, or the underlying substances, have lost electrons through the reaction. If we look at the first example, where magnesium atom loses electrons to become magnesium cation, this is an example of the reactions that metals undergo. If you can recall, metal atoms are not stable. They tend to lose electrons to gain a noble gas electronic configuration. So when metal atoms lose electrons to form cations, this process is actually an oxidation reaction. In the bottom half of the slide, if we look at the ions in red, I hope you can see that they have gained electrons, right? They have added electrons to themselves, and the process is known as reduction, or these ions have been reduced. Now, earlier I mentioned that reduction and oxidation must occur together. So am I contradicting myself here? Because if we look at the examples, it seems like there in the top half there's only oxidation. The ions there are only oxidized. There's no reduction. And in the bottom half of the slide, the ions are only reduced. There are no oxidation reactions or processes. The answer is no. The equations that we see here are not full equations. Okay, the equations that we see here are known as half equations. That means they only show half the reaction. So in order for us to see electron gain or loss by a substance, we can only illustrate by writing half equations, meaning we only show the substance that is oxidized, or we only show the substance that is reduced. But that is only half the reaction. So how do we know what is the overall reaction? We will learn how to combine half equations when we come to the topic of electrolysis, but I will illustrate to you now. For example, if we look at this reaction, right, and this particular reaction. So how do we, there is an oxidation reaction over here where zinc is oxidized to zinc ions, and copper 2 ions are being reduced to copper. This is the reduction. So how do we combine the two equations? Is that we just add the two equations together. We combine the substances on the left and on the right. So on the left of both equations, I have zinc plus Cu2 plus 2 electrons. On the right, if we combine the products for both reactions, we get Zn2 plus Cu plus 2 electrons again. Okay, when writing chemical equation, if a substance appear on the left and on the right of both of the equation, we can actually cancel them off, and the remaining equation is this. Okay, so when we combine the oxidation half equation with the reduction half equation, we get the overall equation. If you look at the overall equation, I hope you can identify what kind of reaction this is. This is actually the ionic equation for a metal displacement reaction. Zinc, being the more reactive metal of the two, displaces copper from its salt solution. So once again, in order to show gain or loss of electrons, we have to split, or we have to write in terms of the half equation. So very often it is not easy in a chemical reaction for us to see what has gained or lost electrons, which brings me back to the point where definitions 1 to 3 are only convenient definitions. You should only use them if it's convenient. So as mentioned, the more applicable definition is definition number 4, which involves the term oxidation state. So right now we're going to learn what is oxidation state. Oxidation state is a number. Alright, it's a number. One way to remember it, how I remember it, is that the number tells us and how oxidized or reduced an atom is in a compound or in an element. Don't worry too much if it doesn't make a lot of sense now, but what is more important now is that we're going to learn how to get the number. Once we learn how to get the number, I will highlight again how the number tells us whether the atom is in a highly oxidized state or in a highly reduced state. Right? The former definition in the syllabus of oxidation state is that it represents the charge of the atom if it were to exist as an ion. Alright, but I find it more convenient to remember it as a number that tells you whether the atom is in a highly oxidized state or in a highly reduced state. Now, in order to obtain the oxidation state or the number associated with each atom, there are 5 rules that we need to memorize or learn to apply. Once we know the 5 rules, we will be able to assign a number or oxidation state to any atom in an element or compound. So the first rule is as follows. So rule number 1, atom in a free element. Element meaning anything that you can find in the periodic table that is not combined with something else. Alright, the oxidation state of the atoms in an element is always given a number of 0. Alright, so these are some examples. Sodium is an element. So oxidation state of sodium is 0. Oxidation state of magnesium is 0. Iron is 0. These are the metals. Now when we look at the non-metals, for example H2, hydrogen gas, is it an element? Answer is yes, because it is not combined with any other elements. Okay, both atoms in the molecule are the same element. Alright, so H2 is considered an element. So each hydrogen atom in the molecule, they are assigned an oxidation state of 0. For oxygen, each atom in oxygen also 0. Each atom in chlorine 0. Each atom in nitrogen 0. I hope you can see now that any atom in an element has an oxidation state of 0. Number 2, if we come across monoatomic ion. What is monoatomic? Mono means one, atomic means atom. So ions that are made up of only one atom, the oxidation state is equal to the charge. So if we look at the examples given, all these ions are only made up of one atom. For example, sodium, Na plus is made up of sodium atom, Mg2 plus is made up of magnesium atom. So what is the contrast to monoatomic ion? Later we will see polyatomic ions. So for monoatomic ions, the oxidation state is equal to the charge. So the oxidation state given to Na plus is actually plus 1, Mg2 plus is plus 2, Fe2 plus plus 2, Fe3 plus plus 3, and so on. Okay, for chloride ion, it has a charge of minus, so the oxidation state is minus 1, and bromide is minus 1 as well. Now in this example, I hope you can see that when writing oxidation states, okay, when writing oxidation states, the charge, we write the charge first, followed by the number. Okay, so we say that the oxidation state of sodium ion is plus 1 and not 1 plus. Okay, and I will tell you why later, but it's very important for you to include the positive sign as well. So we do not simply say that the oxidation state of sodium is 1. We must say that it is plus 1 in the ion. Right? Similarly, we must say that the oxidation state of the copper 2 plus ion is plus 2 and not just 2. Rule number 3, we have seen atoms in elements. What happens when atoms form a compound? When atoms form a compound, when atoms combine with other elements, there are some elements that have a fixed oxidation state, meaning no matter what compound they form, all right, the atom of that element will have a fixed, will always have the same oxidation state. So there are 4 that we need to learn. First is that group 1 elements. All group 1 elements, when they combine with some other element, the oxidation state is always plus 1. All group 2 elements, when combined with any other element to form a compound, the atoms would have an oxidation state of plus 2. Oxygen, when combined with any other element, will have an oxidation state of minus 2. And hydrogen, when combined with any other element, will have an oxidation state of plus 1. Alright, so let's try to apply this rule to the examples given below. Sodium chloride, what is the oxidation state of sodium in sodium chloride? So if you can recall that if sodium is in group 1, so all group 1 elements in compounds are given an oxidation state of plus 1. Second example, magnesium oxide. Magnesium is in group 2. So when group 2 elements combine with any other element, it will be assigned an oxidation state of plus 2. Potassium is in group 1 again, so plus 1. Now, next, hydrogen chloride, HCl. What is the oxidation state on hydrogen? Alright, we can see here that hydrogen is combined with chlorine, so it's no longer an element. It's combined with something else, it is a compound. And when hydrogen forms a compound, it is always, the oxidation state of hydrogen is fixed, it is always plus 1. Same thing in water, H2O. Hydrogen is combined with oxygen. So when hydrogen forms a compound, the oxidation state of hydrogen is fixed, which is plus 1 as well. Okay, in water there are 2 hydrogen atoms. Each hydrogen atom will have an oxidation state of plus 1. Water also contains 1 oxygen atom. So what is the oxidation state of oxygen in water in a compound? It is always fixed to be minus 2. And lastly, when we look at the last example, which is methane. Methane, what is the oxidation state of hydrogen? Once again, hydrogen is combined with some other element in a compound, so the oxidation state is always fixed to be plus 1. Okay, before I go on to the next slide, I just want to recap again. when atoms combine with when atoms of an element combine with another element to form compound, all right, there are certain elements that have a fixed oxidation state. 4 of them, group 1 always +1, group 2 always +2, hydrogen always +1, oxygen always -2. Now, if you have remembered this, now we are going to learn that there are some exceptions to oxygen and hydrogen. Now, these are the exceptions. For oxygen, remember oxygen, when it combines with some other elements, it is always -2. Right? The exception is this. The exception is in hydrogen peroxide. Okay, this molecule is called hydrogen peroxide. In hydrogen peroxide, the oxidation state of oxygen is not -2, but it is -1. So we need to memorize this exception. Whenever you see hydrogen peroxide, the rule that we have just learned just now doesn't apply, but we have to remember that oxygen in hydrogen peroxide has an oxidation state of -1 and not -2. Similarly, for hydrogen, we have learned that when hydrogen forms a compound, the oxidation state is always +1. But there's an exception. The exception is metal hydrides. What are metal hydrides? Metal hydrides are compounds that are formed when a metal combines with hydrogen. For example, sodium hydride or magnesium hydride. Okay, in these two compounds, we can see that a metal has combined with hydrogen. So in metal hydrides, you have to take note that the hydrogen atoms no longer have an oxidation state of +1, but in metal hydrides, the oxidation state of hydrogen is -1. Okay, so in summary, oxygen when formed compound always has a fixed oxidation state of -2, except for hydrogen peroxide where it is -1. Hydrogen, when it's combined in a compound, always has an oxidation state of +1, except for metal hydrides where it has an oxidation state of -1. Now, rule number 4. Rule number 4 is actually a very powerful rule, as we will see later. What is the rule about is that the sum of oxidation state, when we add up the oxidation states of all the atoms in a compound, it is equal to 0. Right? For example, let's look at magnesium oxide. Okay, so magnesium oxide, let's try to assign oxidation states to both atoms. Magnesium is in group 2, so we have learned that when group 2 elements form a compound, it has a fixed oxidation state of +2. Oxygen, we have also learned that when oxygen combines with another element in a compound, it has a fixed oxidation state of -2. So what does the rule say? The rule says that when we sum up the oxidation states, so +2 minus 2, right, it will be equals to 0. So why do I say that this rule is powerful? We can see that in the bottom 3 examples. Alright, let's look at example number 1, magnesium chloride. Okay, MgCl2. Now, if I ask you for the oxidation state of chlorine in magnesium chloride, would you be able to tell me the oxidation state? If we think about it, in rule number 3, does chlorine, group 7, does chlorine have a fixed oxidation state? Answer is no. Alright, so without a fixed oxidation state, how do we know what is the oxidation state of chlorine then? Since we don't know, we let it be X first. Now, does magnesium have a fixed oxidation state? Answer is yes. Magnesium is in group 2, so it's always +2. Now, we can apply this rule in order to find out what is the value of X. How do we do so? we sum up the oxidation states for all the atoms in the compound. So plus 2 plus X, and there are 2 atoms of chlorine. So plus X equals to 0. So if we solve for X, 2X equals to minus 2, X equals to minus 1. So what does that tell us? It tells us that chlorine in magnesium chloride has an oxidation state of minus 1. Okay, let's look at another example. Sodium carbonate. Alright, if I ask you for the oxidation state of carbon, does carbon have a fixed oxidation state? Answer is no again. But are we able to find out the oxidation state of carbon? Answer is yes, by using rule number 4. How do we do it? Sodium has a fixed oxidation state. It is in group 1, so it's always plus 1. Oxygen in compounds, they are always minus 2. And carbon, since we don't know, we let it be X. Now let's try to sum up the oxidation states for all the atoms. So X plus 2 times 1, 2 times plus 1. Why is that so? Because there are 2 sodium atoms, plus 3 times minus 2. Why do we have to times 3? Because there are 3 oxygen atoms. Is equals to 0. Now when we solve for X, we will get X equals to plus 4. So what does that mean? It means that carbon in sodium carbonate has an oxidation state of plus 4. And last example is this, KMnO4. This is known as potassium manganate 7. In the next lesson, we're going to learn more about potassium manganate 7. It's going to be one of the important chemicals that you need to know. Okay, so let's look at KMnO4. Okay, if I ask you for the oxidation state of manganese, how do we obtain the value? Is again by using rule number 4. Potassium is in group 1, so it has an oxidation state of plus 1. Oxygen is in a compound is always given an oxidation state of minus 2. Manganese, we don't know, it's a transition element, so it doesn't have a fixed oxidation state, so we let it be X. Now let's sum everything up. Plus 1 plus X plus 4 times minus 2. Why do we have to times 4? Because there are 4 oxygen atoms, and the sum of oxidation states in a compound, they add up to 0. So if you solve for X, you will find that X equals to plus 7, meaning manganese in potassium manganate 7 has an oxidation state of plus 7. Now before we move on to the next slide, I want you to try to obtain the oxidation state of in another compound, and the compound is this, sodium dichromate 6. Okay, sodium dichromate 6. Like potassium manganate 7, sodium dichromate 6 is going to be one of the chemicals that you have to remember very well later on. So if we look at the formula, I need you to find the oxidation state of chromium. Once again, chromium does not have a fixed oxidation state, so the only way for us to find out the oxidation state is by using rule number 4. And if you have done it correctly, try it first, you would find that it has an oxidation state of plus 6. Okay, so those of you who are sharper, you might notice this, that the Roman numeral, potassium manganate 7 and sodium dichromate 6, the Roman numeral actually tells you the oxidation state on your transition metal atom in the compound. So the last rule that we're going to look at involves your polyatomic ion. Earlier we saw a monoatomic ion being an ion that's made up of only one atom. So polyatomic ion is the opposite. Poly means more than one. Okay, and earlier in chemical bonding, you should have already learned a list of polyatomic ions like nitrates, carbonate, hydroxide, and all this. So these ions contain more than one atom within the ion. Okay, so what is the rule? The rule is that if we sum up the oxidation states for all the atoms in the ion, is actually equal to the charge. So how is that useful again? If we look at example number 1, sulfate, SO4 2-. Does sulfate have a fixed does sulfur in sulfate have a fixed oxidation state? Answer is no. And how then do we obtain the oxidation state? We can use rule number 5. So once again, we let it be X. Oxygen in a compound or combined with any other element has a fixed oxidation state of -2. So when we sum everything up, X plus 4 times -2, once again, why times 4? Because there are 4 oxygen atoms, is equal to the charge on the ion, which is -2. So if we solve for X, we will get X equals to +6, meaning the oxidation state of sulfur in sulfate is actually +6. Next example, we'll look at nitrate, NO3-. So nitrogen is in group 5. Does it have a fixed oxidation state? Answer again is no. So we let it be X. Oxygen, when combined with any other element, is always given an oxidation state of -2. So let's try to sum everything up. X plus 3 times -2 equals to the charge, which is -1. And when you solve for X, X equals to +5. Alright, again, meaning the oxidation state of nitrogen in nitrate ion is +5. The last example, we have NH4 plus ammonium ion. So we want to find the oxidation state of nitrogen in ammonium ion. Nitrogen is in group 5. Does it have a fixed oxidation state? Answer is no. So we let it be X. Hydrogen, when combined with any other element, is always given an oxidation state of +1. So in order to find the value of X, we can sum up all the oxidation states. X plus 4 times +1 equals to the charge, which is +1. And when you solve for X, you'll find that X equals to -3. So through the examples, I hope you can see how rule number 4 and number 5 is very powerful in allowing us to know the oxidation states of elements where they do not have a fixed oxidation state. Right. Also from this example, I hope you can see that we have nitrogen in examples 2 and 3. But in example 2, nitrogen has an oxidation state of +5. And in example 3, nitrogen has an oxidation state of -3. So that serves to highlight that certain elements, when combined in compounds, they do not have a fixed oxidation state. So they can exhibit different oxidation states in a compound. The only ones that are fixed would be your group 1, group 2, oxygen and hydrogen. Next, before we go on to look at real examples, I just want to point out again the definition of oxidation state. As mentioned, it is a number that tells us how oxidized or how reduced an atom is. So when an atom has a positive oxidation state, it means that it is in an oxidized state. When an atom has a negative oxidation state, it means that it is in a reduced state. Okay, the larger the number, the more oxidized or reduced the atom is. Okay, so therefore the sign carries a meaning. Plus means oxidized, minus means reduced. Therefore, even if it's a positive number, you're expected to write plus something, +3, +4, right? Without the plus, the oxidation state do not carry the full meaning. So now that we have learned how to obtain oxidation states, the 5 rules that will allow us to assign oxidation states to any atom, let us look at the last definition. The last definition states that a substance is oxidized when the oxidation state increases in the reaction, whereas a substance is reduced when the oxidation state decreases through the reaction. So let us try now to identify the substance that is oxidized and the substance that's reduced in this particular example. And we can do it by assigning oxidation states to all the atoms in the reactants and products. So when assigning oxidation state, usually I have a practice to look out for the elements and assign the oxidation state of 0 first. So for this reaction, there are 2 elements. Zinc is an element, so we assign an oxidation state of 0. Copper is an element, so we assign an oxidation state of 0. Next, for copper 2 oxide. Copper 2 oxide, does copper have a fixed oxidation state? Answer is no. Copper is a transition element. It doesn't have a fixed oxidation state. Oxygen, when combined with any other element, has a fixed oxidation state of -2. Okay, so invoking rule number 4, when we sum up the oxidation states in a compound, it should be equals to 0. That will allow us to determine the oxidation state of copper to be +2. The same rule applies to zinc oxide. Oxygen in a compound has an oxidation state of -2. Zinc doesn't have a fixed oxidation state, but we know that if we sum up the oxidation states, it must be equals to 0. So the oxidation state of zinc is +2. So by comparing the oxidation states, we can see that zinc has been oxidized. Zinc atom has been oxidized because the oxidation state increases from 0 to +2. Whereas copper atom has been reduced because the oxidation state has decreased from +2 to 0. So a common question that you will get is this: which substance is oxidized and which substance is reduced? To answer this question, there is a recommended template that you need to remember. So the substance that is oxidized is zinc. So zinc is oxidized, and we need to explain how do we know, since the oxidation state of you need to state the atom that has been oxidized. So the atom is zinc, has increased from 0 in which substance, which is zinc, to +2 in which substance, which is zinc oxide. Similarly, for which substance is reduced, we can use the same template. This is the common mistake that students will make. Students will say copper is reduced. Yes, copper atom has been reduced, but when they ask you for which substance has been reduced, you need to write down the whole substance, which is copper 2 oxide. So copper 2 oxide is reduced since the oxidation state of which atom? Copper atom has decreased from +2 in which substance, which is copper 2 oxide, to 0 in which substance, which is copper. Okay, so as mentioned, when answering questions like this, please make use of the template, because if not, you will run the risk of missing out some important information in your answer, which will not give you full credit. Okay, in the next slide, we will see the template, so please take down the template and use it in your answers. So in order to answer questions like this, first you need to write the formula or the name of the substance, the whole substance, remember, and not just the atom or the element that has been oxidized or reduced. Okay, since the oxidation state of the element or the atom that has been oxidized or reduced has changed from the initial oxidation state in what substance to the final oxidation state in what substance. If you follow closely to this template, you will be able to get full credit for such questions. Otherwise, if you miss out anything, for example, if you don't write the oxidation states or the compounds, then you run the risk of losing marks for such questions. So once again, using the template, zinc was oxidized since the oxidation state of the element or the atom that has undergone the redox. Zinc has increased from 0 in Zn to +2 in ZnO. And CuO, the whole substance, copper 2 oxide, was reduced since the oxidation state of copper has decreased from +2 in copper oxide to 0 in copper. Now we look at another interesting example here. This is a reaction which is the decomposition of hydrogen peroxide. So decomposition is when you have a substance breaking down into 2 or more products. So hydrogen peroxide is actually not very stable, so it actually decomposes to form water and oxygen gas. Now this reaction is redox in nature. So I'll need you now to assign oxidation states to all the atoms and find out which substance has been oxidized and which substance has been reduced. So once again, we will try to assign 0 to any elements that we see there, and indeed there's an element which is oxygen, so 0. So the 2 oxygen atoms in oxygen gas both have an oxidation state of 0. Next, if we look at hydrogen peroxide, after viewing the video, the name should scream at you that hydrogen peroxide, there is an exception to oxygen. Oxygen in hydrogen peroxide doesn't have its usual oxidation state of -2, but it has an oxidation state of -1. Okay, hydrogen in hydrogen peroxide is still your usual oxidation state of +1. Then we look at water. In water, hydrogen when combined with any other element is always +1. Oxygen when combined with any other element is always -2. So now that we have obtained the oxidation states of all the atoms, let's see. Oxygen had an oxidation state of -1, but it became -2 in water after the reaction. So we say that hydrogen peroxide has been reduced. But then we look again. Oxygen has an oxidation state of -1, but through the reaction, it seems to have increased to 0 in oxygen. So we say that hydrogen peroxide has been oxidized as well. How do we use the template to write out? So hydrogen peroxide was oxidized since the oxidation state of the atom, which is oxygen, has increased from -1 in H2O2 to 0 in oxygen. Similarly, hydrogen peroxide was reduced since the oxidation state of oxygen decreased from -1 in hydrogen peroxide to -2 in water. So before I go on to address a very unique situation here, I just want to mention a few things that students will often ask. Do we need to consider the reacting ratio when computing oxidation states, or when accounting for oxidation and reduction? Answer is no. If you can recall, reacting ratios are only important in chemical calculations. Alright, it tells us the preference or the ratio in which they like to react in. But when we talk about a substance, we don't have to care about the ratio in which they like to react in. Alright, so in assigning oxidation states, in identifying substances, we ignore the reacting ratio. We only make use of the reacting ratio when we are performing chemical calculations. The second question that I always get, or common mistake, is this, that students assign the oxidation state of hydrogen to be +2. Alright, why? Because there are 2 hydrogen atoms there. But bear in mind that oxidation state is assigned to individual atom. Okay, so even though there are 2 hydrogen atoms there, we say that the oxidation state on hydrogen is +1 because it's assigned to individual atoms. Next, the unique situation here is this. In the previous examples, we saw that the substance that was oxidized and the substance that is reduced are 2 different substances. But in this example, the same substance, hydrogen peroxide, was oxidized, hydrogen peroxide was also reduced. Now for a unique reaction like this, where the substance that's oxidized and reduced is the same substance, we give it a special name. It's called disproportionation. Okay, so this proportionation reaction is a redox reaction in which the same substance is both oxidized and reduced. So some things to note when we are assigning oxidation state is that oxidation state is assigned to individual atom. I've mentioned this before. So it's not correct. Some students will say, hey, everything seems to be 0. What? Isn't the oxidation state of water 0? It's not correct. The sum of oxidation states in water is 0, but the oxidation state is assigned to individual atom. We do not assign oxidation states to a whole compound. Alright. Secondly, as mentioned, ignore reacting ratio when assigning oxidation states. Reacting ratios are only important in chemical calculations. And I hope you have noticed by now, the substance that's oxidized or reduced must always be on the left of the equation. Okay, it doesn't make sense that the substance that's oxidized or reduced is a product, right? Because it has undergone reaction, reactants undergo reaction, so the substance that's oxidized or reduced must be a reactant. Right? Despite having said that, whenever we ask which substance is oxidized or reduced, there will be students who write a substance that is a product, which is immediately obviously wrong. Now, another common type of question that you will get is that you get a whole list of reactions and they ask you to identify which reactions are redox and which reactions are not. So it's very useful for you to remember that there are 3 types of reactions that are not redox in nature. And the 3 types of reactions are acid-base reactions. So when you see acid reacting with a base, such a reaction is not redox in nature. Precipitation reactions are not redox in nature. And decomposition reactions, thermal decomposition of your metal carbonates, they are not redox, usually not redox in nature. So that will help you very quickly identify reactions that are not redox in nature. Now, if you don't believe me, you can assign oxidation states to all the atoms and then you find that they have not changed at all. Okay, so to identify redox reactions, what we can do is we can cancel away reactions that are obviously not redox, like acid-base, precipitation, and decomposition. Okay, now I'm going to teach you another method that is much faster but will only work in the O-level context. Meaning if you go to A levels or higher levels, this unique hack will no longer work in identifying redox reactions. So before I teach you the hack, this is what I was saying, that you're given a list of reactions and you need to quickly identify, especially in an MCQ paper, which reaction is redox and which reaction is not. So the hack is this, that if you spot any element in the reactant or product, okay, if you spot any element in the reactant or product for a reaction, it is confirmed redox in nature. Alright, So if we look at the list, reaction, let's number the reactions. Reaction 1, do you see any elements in there? Answer is yes, so it's redox. Reaction number 2, do you spot any elements in there? Yes, so it's definitely redox. Reaction 3, there's also an element in there, so it's redox. Reaction 4, redox. Reaction 5, also redox. Reaction 6, do you spot any element in there? Answer is no, there are no elements in reaction 6, so it's not redox in nature. And reaction 7, do you spot any element in there? Answer is no again, so it's not redox in nature. Alright, so in O levels, if you are required to identify a redox reaction, just look for a reaction where there's an element in the reactant or product. Okay, so if in case it's not clear enough, I'm going to underline the elements in the redox reactions for all of them. Reaction 1, these are the elements. Reaction 2, these are the elements. Reaction 3, reaction 4, reaction 5, and that's all. Okay, so once again, to spot a redox reaction, just look for a reaction where there is an element in the reactant or product. So in the context of O level, that reaction is definitely redox.